Howdy, welcome to Math 153, Elementary Statistics. I am Lance Curtis. This is the lecture for sections 7.3 and 7.4. As you can see, the final two sections, we're going to continue on with our theme of estimating a population parameter. In this next section, we're going to focus on estimating the population mean. So the key concepts in this section are what you see here on the screen. So we're going to present methods for using the sample mean to infer the value of the corresponding population mean. As we saw previously in Chapter 6, the sample mean will be our best point estimate of the population mean. We can use sample data to construct a confidence interval for estimating the value of a population mean, and there is a correct way to interpret that interval. We can determine the sample size necessary for that estimate, and making inferences with the sample mean will require a normal distribution. So this means one of two things. Either the data itself must be normally distributed at the start, or a sample size must be greater than 30. Because if the sample size is greater than 30, then central limit theorem says we can use a normal distribution to approximate a non-normal distribution. So when we're trying to estimate a sample mean, we're using a sample mean to estimate a population mean, there is a key question that we need to ask. Do we know what the population standard deviation, sigma, is? If the answer to that question is yes, then we want to use a normal distribution for our estimation to calculate a critical value z-score. If we don't know what the population standard deviation is, then we need to use a student t-distribution and calculate a critical value t-score. Now these answers assume that the data is either normally distributed to start with or has a sample size greater than 30. So looking at these two options, we're familiar with the normal distribution. We know about calculating z-scores. But what's this student t-distribution all about? Well, let's look at that. So, if the distribution of a population is essentially normal, then the distribution of t-scores is a student t-distribution for all samples of size n. Basically, the student t-distribution, also referred to as the t-distribution, is what you see here in the graphic. And it resembles, in many instances, shape and properties of a normal distribution. There are some important differences, however. We'll get into those in a moment. First, you need to understand that we use t-distributions to find critical values denoted by t sub alpha over 2. So instead of calculating z-scores, we're going to calculate t-scores because it's a different distribution. We calculate those t-scores with this equation. Notice the similarity between this equation for t-score and the equation we were using earlier to calculate a z-score. Very similar in form. Now, as far as properties of the student t-distribution are concerned, as I said, in many respects it resembles the normal distribution. But there are some important differences, one of which is the t-distribution will actually be different for different sample sizes. So here in this graphic, you see that we have different degrees of freedom. This is another aspect that's different. Degrees of freedom are related to the sample size, as we'll show previously. So as we increase sample size, we increase degrees of freedom. And notice how, as we get closer to the normal distribution, we're actually adding on extra degrees of freedom. Now we have the same general bell curve shape that the normal distribution has here on the outside. But if we look at this t-distribution with only 1 degree of freedom, notice how the tails are elevated above the tails of the normal distribution. And notice how the center section is actually shortened considerably. So this combination that changes the shape slightly of the t-distribution accounts for greater variability that we would expect to see with smaller samples. And it was for smaller samples that this particular distribution was originally developed. Just like the standard normal distribution, we have a mean value of 0. So t equals 0 is at the center of the t-distribution, just like z equals 0 is at the center of the standard normal distribution. The standard deviation of the student t-distribution can vary. It can be pretty much whatever we want, but it is directly connected with sample size. Typically, it's greater than 1. Okay, this is not like the standard normal distribution. Standard normal distribution always has a standard deviation of 1. So there is a difference there. Notice that as the sample size gets larger, the student t-distribution will get closer and closer to the normal distribution. Okay? So this is why, if we don't know what the population standard deviation is, we use the t value and not the z value, because this t-distribution accounts for more variability than we would see with a smaller sample. And if we don't know what the population is, then perhaps we do have a small sample. Perhaps we don't. But the t-distribution actually provides a better approximation when we don't know what the population standard deviation is. I talked about degrees of freedom, so let's try to explain this concept a little bit. The t-distribution will use all the same nomenclature that we've used with the standard normal distribution and z-scores, but there is one addition: degrees of freedom. So the degrees of freedom for collection of sample data is simply the number of sample values that can vary after certain restrictions have been imposed on all data values. For most distributions, what this turns out to be is that we abbreviate degrees of freedom with df, and then we simply take 1 away from the sample size, and that's our degrees of freedom. So for the t-distribution, df is going to be equal to n minus 1. This is all you really need to understand about degrees of freedom. Conceptually, it's not much use at the elementary level that we're studying in this course. It actually comes into play a lot more if you go further on. But for the purposes of this course, all you really need to understand about degrees of freedom is that it's 1 less than the sample size. This brings us to constructing confidence intervals for the mean. Now remember, the key question we had earlier was, do we know what the population standard deviation is? So we're going to need to look at each case. The case where we do know what the population standard deviation is, and the case where we don't know what the population standard deviation is. Let's look first at the case where sigma is unknown. When we don't know what the population mean is and standard deviation is, we can use the t-distribution to construct a confidence interval. Okay? Notice we have the same format for constructing confidence intervals for means that we had for constructing intervals for proportions. It's just the variables in our format here resemble means as opposed to proportions. But it's the same essential concept. So we're going to construct this confidence interval the same way as we did with proportions. Of course, there are some minor modifications. First, because we're using the t-distribution, our margin of error E is going to be calculated with this formula here, with the addition that we have n minus 1 degrees of freedom. The critical values, t alpha over 2 and t-scores, we're going to calculate them either using a table or we'll use software. And no matter which of these methods we pick for calculating our critical values and t-scores, we're going to use n minus 1 degrees of freedom. So the steps for constructing the confidence interval are: first, we must verify that the required assumptions are satisfied. Our methodology here has certain assumptions behind it. The first is that the sample must be a simple random sample. Next, the population is normally distributed. We're assuming that that's true. If, however, that's not the case, then we need a sample size greater than 30, so that per central limit theorem we can then use a normal distribution to approximate. Once we verified that the assumptions are satisfied, we need to find the critical value t sub alpha over 2 corresponding to our desired confidence level and n minus 1 degrees of freedom. Then we calculate our margin of error, find the values of our lower and upper limits, and place them in the general format for our confidence interval, and then round as appropriate, usually to 3 significant digits. So let's look at an example involving garlic and cholesterol. It's commonly claimed that garlic lowers cholesterol levels. So in a test of the effectiveness of garlic, 49 subjects were treated with doses of raw garlic, and their cholesterol levels were measured before and after the treatment. So now we're going to see if the garlic had any effect on their cholesterol level. The changes in their levels of LDL cholesterol were calculated to have a mean of 0.4 and a standard deviation of 21. So with this information in hand, now we use the sample statistics, sample size of 49, sample mean of 0.4, and sample standard deviation of 21 to construct a 95% confidence interval estimate of the mean net change in LDL cholesterol after the garlic treatment. And then the question we're asked is, what does the confidence interval suggest about the effectiveness of garlic in reducing LDL cholesterol? All right, well, let's look at that. The first thing we need to do is get our critical value, which, if we're using a table, we'll get something that looks somewhat like this. All the values in the t-table, it doesn't matter what t-table you're using, all the values in the t-tables are pretty much the same. What differs is the values that you see for degrees of freedom here on the left side, and the column headings up top, which represent your alpha. So this is the area underneath the tails. Some t-tables, like the one that you see here on the screen, are one-tailed t-tables. In other words, the headings that you see at the tops of columns are listing the area in one tail. Some t-tables list two-tail areas for column headings. Other t-tables list both two-tail and one-tail. So it doesn't matter which you have. You can use any of them. You just have to know how to maneuver around with it. So first we need to get our alpha level, which we get from our 95% confidence interval. That's what we want, 95% confidence interval. So that 95% confidence level says alpha is 0.05. Now, our critical value, t sub alpha over 2, implies we need a two-tailed area equal to alpha. Alpha over 2, so that alpha area is split amongst two tails. Well, here, our table is a one-tailed t-table. So if we have the two-table, then we just look for the 0.05 at the top. But since we don't have the two-tail table here, these are one-tailed table headings, then what we do is we divide our alpha by 2, so we get that alpha over 2. That gives us 0.025, and then we just look for the column heading 0.025. That's this column right here. So this column contains the value that we're looking for. Now, in our example, n equals 49. So that means we have 48 degrees of freedom. But if you look over at the side of the table, 48 is not listed. You go 40 and then you jump up to 50. So this presents us with a couple of choices that we can make. First choice we could make is to interpolate. So we would go over here, take the value for 40, take the value for 50, and then interpolate between those two, and we do that math, we get 2.011. But since I'm a lazy engineer, I would look at this and say, okay, 48 is not that far from 50, so I'm just going to take the value here that's listed in the row for 50. So if I look at this row for 50, the intersecting value here, 2.009, that's the one I'm going to just grab for my calculations, and I don't have to do the math involved with the interpolation. Notice that this approximation I'm using, because 48 is close to 50, the t-score I'm getting is not all that different. So 2.009 is not all that different from my interpolated value of 2.011. So this looks to be a pretty good assumption I'm making with the 48 being close to the 50. Now that I have my critical t-value, I can calculate a margin of error. Here's our equation for margin of error. We substitute in what we know. Here's our t-value. Notice I'm using the estimated one from that row of 50 degrees of freedom, even though we really have 48. Here's my sample standard deviation divided by the square root of my sample size, 49. And when I punch all this out, I get 6.27. Now, if I had actually used that interpolated value corresponding to 48 degrees of freedom, I would get a margin of error of 6.033. That's not a whole lot different than 6.027. Okay? So again, we see that just grabbing that value that's close by is serving us okay. Now we've got our margin of error, we're ready to construct our confidence interval. So here's the general format for a confidence interval. We substitute in our values for our sample mean and margin of error. So subtracting to get the lower bound, adding to get the upper bound, and out comes negative 5.627 to 6.427. Notice that if we use the interpolated value, we get negative 5.633 to 6.433. So up to 2 decimal places, we have an equivalent 95% confidence interval. So using that, just grabbing that value instead of doing the interpolation, seems to be working out okay for us. So we're just going to say this is our confidence level at confidence interval of 95% confidence level. This means we're 95% confident that the limits of negative 5.6 and 6.4 actually contain the value of the population mean mu, which is the mean of the changes of LDL cholesterol for the population. Now, because the interval value that we have here does contain the value 0, that means it's highly possible that there is no change in the LDL cholesterol level due to the garlic treatment. And if there's no change, then we can't conclude that the garlic treatment is effective in lowering LDL cholesterol. So that becomes our conclusion. We don't have the evidence to support the claim that garlic treatment lowers LDL cholesterol. Let's consider now the case where we do know what sigma is. So if we do know what sigma is, then we can use the actual z-tables, and just like we've done before with the normal distribution. So we notice we have the same format for constructing our confidence interval that we did with sigma being unknown, but now we're going to use a different way of calculating our margin of error. So notice how this equation for margin of error resembles the one we were using earlier. We're just replacing the t-score with a z-score. Notice how, because we're using the normal distribution, we don't have to worry about any degrees of freedom. So we'll find these critical values, z alpha over 2 and z-scores, using either a table or software, just as we've done previously. Here's an example that we can look at about boat redesign. So over the years, the mean weight of men has been on the rise. This means we need to redesign boats with an updated mean estimate so that they don't become dangerously overloaded. There have been incidents where people have gotten into boat accidents and died because an obsolete estimate of the mean weight of men was used in designing the watercraft. So let's first obtain a sample. Let's say we get a sample size of 40. The sample mean is 172.55 pounds. We've used a simple random sample, so we've got that assumptions for constructing our confidence interval satisfied. And then to get this actual standard deviation for the population, we actually did some research amongst several sources which suggested that sigma was equal to 26 pounds. So this is the value we're going to use for sigma. Now, with all of this information collected, we're asked 3 items. First, find the best point estimate of the mean weight of the population of all men, construct a 95% confidence interval estimate, and then what do the results suggest about the mean weight of 166.3 that was used to determine the safe passenger capacity of water vehicles back in 1960. So let's tackle these first two questions first. The first question was, find the best point estimate of the mean weight of the population of all men. Well, we know that the best point estimate for the population mean is the sample mean. And we have the sample mean already. So the sample mean of 172.55 pounds is the best point estimate of the population mean. The second item we were asked to attend to is to construct a 95% confidence interval estimate of the mean weight of all men. So 95% confidence interval, that means that alpha is going to be equal to 0.05. So we know from our previous chapter that corresponds with a critical z value of 1.96. With this value, we can now calculate our margin of error. So here's our equation. We substitute in what we know. There's our critical z-score, sample standard deviation, and sample size. Punch that out on your calculator and you get 8.057. Now we have everything we need to construct our 95% confidence interval. Here's the format. We substitute in our values for x bar and e, and out comes 164.493 to 180.497. This then is our 95% confidence interval estimate. Now, the third question we were asked, what do the results suggest about the mean weight of 166.3 pounds that was used to determine the safe passenger capacity of water vessels in 1960? Well, we found earlier on the previous slide that 95% confidence interval is 164.493 to 180.497. So, looking at this confidence interval, it's possible that the mean weight that was used back in 1960 of 166.3 could still be the mean weight of men today. It's inside our 95% confidence interval. That being said, our best point estimate, which is the sample mean, is also within this 95% confidence interval, and it's greater than 166.3, the value that we get from back in 1960. So, considering that both of these estimates are located within our confidence interval, this suggests that what we really need to do is go back and get some more data. We don't have enough data to make an accurate conclusion about the need for redesigning boats. That's because the old value that was used in the design, which is actually leading to accidents today, is in our confidence interval, and the value that should be used today, which is coming from our sample, is also within our confidence interval. So they shouldn't both be in our confidence interval. It should be, the one should be in and the other should be out. But because both of them are in, that suggests we don't have all the information we need. Perhaps we need to go back and do some more looking into what the population standard deviation is. We simply did some research and several sources were suggesting it to us, but perhaps we need to do something a little bit more definitive than simply grabbing a number that somebody else used. So there may be some more work involved, but either way, we need more information in order to ferret out this situation. We can calculate sample sizes, the minimum sample size that we need to estimate a population mean. We're going to use the same equation. We just, not the same equation from proportions, but we just use the same methodology to get the equation. So we're going to use the same equation we use for margin of error and just reorganize it in terms of n. And this is what we get when we do that. Now, notice that this requires us to know the population standard deviation. When we get the answer, we're always going to round to the next whole number. But what if we don't know what the population standard deviation is? Well, that means we have three options. The first option we can take is to use the range rule of thumb to estimate the standard deviation. So if we take our range Remember that the range is basically 2 standard deviations on either side. So if we take the range and divide it by 4, then that gives us an estimate for the population standard deviation. Alternatively, we can use an iterative approach. So we collect the first few samples, collect and then calculate our sample mean from that information that we've already collected. And then as we collect more data, get more samples, we can refine that calculation and use it as an approximation to estimate our population standard deviation. We can use the results of an earlier study, just as we did in the previous example, to estimate our population standard deviation. So there are different options presented to us, and depending on the context, some of these options may be better than others. That is something that you will determine only with experience. As you get experience actually working this sort of thing, you come to understand which path is the path that you need to take. Let's look at an example involving IQ scores. IQ scores tend to be normally distributed. Let's assume that we want to estimate the mean IQ score for the population of statistics students. So how many statistics students must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? Okay, so a 95% confidence level means that alpha is 0.05, which means our critical z-score is 1.96. Now, we're going to use a previous study to get our population standard deviation. It suggests that sigma is equal to 15, so that's what we're going to run with. Here's our equation for calculating population, or excuse me, the sample size that we need to estimate the population mean. We plug in what we know. There's our critical z-value, the population standard deviation, and the margin of error, which is 3. Notice that it's not a decimal. It's 3 because we want within 3 IQ points, not 3 percentage points. Punch that out in your calculator and you get 96.04, which of course will round up to 97, and this then is our minimum sample size. So with a simple random sample of only 97 statistics students, we will be 95% confident that the sample mean is within 3 IQ points of the true population mean, mu. That takes us to the end of section 3. Now, let's jump into the last section, section 4, estimating a population standard deviation or variance. We're going to find that among the key concepts, many of the methods that we're presenting here are just the same as what we've seen for mean and proportion. But there is a big important difference, and that is we need to use the chi-square probability distribution to construct our confidence interval. Now, you're probably wondering, what's the chi-square distribution? Well, if you remember back to our earlier dice rolling experiment that we conducted in the previous chapter, okay, remember that when we assembled all of the samples together, so we rolled 5 dice, and we had, 100 trials, 1,000 trials, 10,000 trials. And when we got up to 10,000 trials and put all the samples that we had collected into a distribution, the samples for the variance were forming a skewed distribution as opposed to the normal distribution that was formed when we collected the sample means and sample proportions. So we model the skewed distribution with a chi-square probability distribution. This is what allows us to model the skewed distribution. We calculate a chi-square statistic with this equation here. Now, I know this looks like the letter X, but this is actually the ancestor of our English letter X, the Greek letter chi, hence the name chi-square, because this is chi squared. So you see we have degrees of freedom multiplied by the variance of the sample divided by the variance of the population. Again, degrees of freedom is equal to n minus 1. N is our sample size. So because it's a skewed distribution, the chi-square distribution is not symmetric. Okay, the normal distribution is symmetric, the student t-distribution is symmetric, but the chi-square distribution is not symmetric. It is skewed. However, the values of the chi-square can be 0 or positive, but it can never be negative. Okay, so it does share that in common with the normal and student t-distributions. Okay, the values we get out of the distribution are always positive or 0. They're never negative. This density curve never goes below the horizontal axis. Now, just like we saw with the t-distribution, chi-square distributions are different depending on your degrees of freedom. Okay, and we can see here in the graphic that as we increase our degrees of freedom, notice how the shape of the curve becomes less and less skewed and more centered, symmetrical about the mean, and approximating that normal distribution. So it shares that property with the student t-distribution. As the number of degrees of freedom increase, the distribution will become more symmetric, and it will start to approach a normal distribution. Now, for low values of degrees of freedom or sample size, the distribution is highly skewed. And so, because of that, we need to calculate 2 critical values, and not just one. So there's going to be one bordering the tail we have on the left side of the distribution, and there's going to be another one bordering the tail we have on the right side of the distribution. So we have chi-squared sub L and chi-squared sub R. 2 critical values. Okay. Now, because variance is an unbiased estimator, the best point estimate of the population variance is the sample variance. So we'll use that in constructing our confidence interval for variances. Now, when it comes to sample standard deviations, we'll typically use those as the point estimate for our population standard deviation, even though it's a bias estimator. We're actually, it's a biased estimator, but we're going to use it because it's a lot easier to use this than to try to use something else or to make more adjustments that would make it a better target for our population parameter. So we'll actually, and using the chi-square distribution tends to work out pretty well okay. The key is to construct first for variance. So we're going to construct our confidence interval for variance, whether we want a confidence interval for variance or a confidence interval for standard deviation. It takes this form that you see here. So we've got our chi-squared statistic forming the lower and upper bounds, but notice how we're using the critical value from the right tail in the left side of the confidence interval and the critical value from the left side of our distribution in the right side of our confidence interval. They're flip-flopped. Now, you would ask, why would we flip-flop? Why would we not use the one on the right for the value on the right and the one on the left for the value on the left? As we work through an example that's coming up shortly, I'll make this apparent to you. It'll become apparent. This is why we actually do that. For now, just walk a little bit on faith that this is the way it should be. Now, because standard deviation is the square root of the variance, okay, we simply construct the confidence interval for standard deviation by constructing the confidence interval for variance, and then we just take the square root of everything. Okay, this is a much simpler procedure than trying to go at it an alternative way. So even though the standard deviation is a biased estimator, we use an unbiased estimator of the variance to get us the confidence interval for the variance. So we're pretty solid on that. And then we simply take the square root to get the standard deviation. This is a much simpler procedure than what we might otherwise do. Constructing the confidence interval for variances and standard deviation follows a similar pattern that we've seen before. First, verify that our assumptions are satisfied. Okay, the sample must be a simple random sample. The population must be normally distributed, no matter how large the sample is. So whereas where we were using that t-distribution, we could actually substitute in and say, well, if it's not normally distributed, central limit theorem says that if the sample size is greater than 30, we're still good. Here we don't have that option. Why? Because the chi-square distribution is not symmetrical about the mean. It's not a normal distribution. It is a skewed distribution. And so we don't have that option of, well, if it's greater than 30, we can just go ahead and just approximate it with the standard normal distribution. We don't have that. Now, as you increase the sample size and the degrees of freedom, you will approximate a normal distribution with the chi-square distribution, but in many instances, you're not going to have that. So that central limit theorem that we were using before to say if it's not normal, we can get away with using the normals at approximation, that doesn't work here. So you've only got these two assumptions. The sample must be a simple random sample, and the population must be normally distributed. Then we find our critical values, one on the left side, one on the right side, that correspond with our desired confidence level and degrees of freedom. Calculate our lower and upper bounds. If we want a confidence interval for the standard deviation, remember we take the square root of the lower and upper bounds that we calculated for variance, and then we round as appropriate per whatever the convention of the day is. Typically, what we're going to do is just use one more decimal place than the original data. But again, that could change depending upon where you're at and who you're with. So just follow the convention that's in play for whatever you're doing. Let's look at an example involving IQ tests. As we mentioned previously, IQ scores are typically normally distributed, but we're going to look for standard deviation. So a group of 22 subjects took an IQ test during part of a study. And these subjects, the 22 of them, had a standard deviation IQ score of 14.3. So now, assuming the data is normally distributed, construct a 95% confidence interval estimate of sigma, the standard deviation of the population from which the sample was obtained. To do that, we need to find our critical values. We either do that using a table like we just did for t-scores, and many of the chi-squared tables are organized in a similar fashion to that of the t-tables. So if you want, you can use a chi-square table, or you can use software, get your critical values out. Either way, your lower critical value will be 10.283. Your upper critical value, the one on the right, will be 35.479. Now with the critical values in play, we can construct our confidence interval. So here's our format. Notice I'm already taking the square root of everything from our variance equation to get the standard deviation. That's what we're looking for. Plug in what I know. So there's 22 subjects, which means we have 21 degrees of freedom. Sample standard deviation, 14.3. And the values that you see here are the critical values that we get from our chi-square distribution. Notice the bigger one goes on the left. The lower one goes on the right. Okay? This gives us 11 to 20.4. This then is our confidence interval with 95% confidence level. Notice that if we swapped these values around, then the values we get out for our upper and lower limits would be reversed, because the upper portion of our fraction on each side of our confidence limit is exactly the same. So the only difference is what's in the bottom of the fraction. So if we actually put the lower one, the one we get on the left side of our distribution, on the left side of our confidence interval, and vice versa with the right, then the 20.4 would be on the left and the 11.0 would be on the right. That would reverse the order that we typically have, with the lower limit going on the left and the upper limit going on the right. So in order to preserve the order, you've got to have the lower number being divided out to give you the upper bound, and the higher number dividing out to give you the lower bound. This is why they're flip-flopped. Now, based on this result, we have 95% confidence that the limits of 11 to 20.4 contain the true value of the population standard deviation. Sample size. Now, earlier we were using equations to calculate sample size. Because we have a chi-square distribution and it is skewed, and the shape of it changes radically depending upon how many degrees of freedom that you have, the procedure for calculating an equation is much more complicated than what we really want to go through. So what we're going to do when we calculate sample sizes for estimating variances in standard deviation is to use a table like the one you see here on the screen. So let's look at an example that involves that. We want to be 95% confident that our estimate of the standard deviation sigma of all voltage levels in a home is within 20% of the true value of sigma. Okay, so how large should the sample be? We're asked to assume that the population is normally distributed. Now we've got our initial assumptions satisfied. So to get the actual sample size, we're just going to use our table that we saw on the previous screen. So the first step is locate the section for 95% confidence on your sample standard deviation. Here I have it blown up on the right side of your screen. So this is the top left corner of what we saw on the previous slide. Now that we've got the right section, we find the row for an error of 20%. So there on the left you can see, different percent values. We want to be, 95% confident within certain percentage levels. Find the row for 20% and then read off the minimum sample size right there to the right of it. We see that it's 48. So this then says that we should obtain a simple random sample of at least 48 voltage levels from the population of voltage levels. That's all there is to it. You're just reading a number right off a table. And let me tell you, that appeals to the lazy engineer in me. And that brings us to the end of this lecture. So if you have any questions, you know how to get a hold of me. Otherwise, I will see you in class. Thanks for watching.